density doesn't matter. Like if you have more particles in a
Dude, it's frozen.
tighter space, it would be like
It's more ordered in that tighter
Because
space.
he's still.
there wouldn't be like much like cluster as to kind of spread out.
Yes, but there's more possible positions like this, more disordered than it is like this. And if we keep cramming this thing together, it's got to be more and more ordered. So yeah, we're looking for disorder or randomness or chaos. And it's the bigger your box, the more disordered they are. Freddie?
When you say like there's only a certain number of ways you can arrange the particles of the container on the left, do you mean like a very large number of ways, but the one on the right is like even larger?
Yeah, when I say there's only a certain number of ways, yeah, there's many, many ways you could arrange this, but there's even more arranging it this way. Yep.
Like when you say arrange,
Is this a filibuster to avoid the derivation? Is Carthy going to pay you guys?
when you say arrange, like is it talking about like arrangement in relation to like the different to the other ones, to the other items, or is it like in relation to the system?
In relation to the other atoms. Because they have to be inside the box.
So like
right?
how close they are or how far they are.
Yeah. Venki. Last question, then we got to do this.
Does the shape of the container change, like, the entropy? Like, if they were the same volume, but one of them was like a cube and the other one was a sphere, would it change?
That's a good question. No, if they're the same volume, regardless of the shape, they'd be considered the same entropy.
So what if it was like one atom then wouldn't there only be one possible?
All right, so you got me, Venki. That's a very good point. Does everybody hear what he's saying? If the container is the same volume, but it's only one atom thick, so it's real thin, but it's spread out, you can't have that many arrangements.
Wait, what?
Okay.
It's going to be a lot more spread out, like 10 to like the something in power.
Right, yeah, but then it's not like cubic, right? So it's a linear way.
So,
Okay, so you found a flaw in the definition of
wait, no,
entropy.
that should be right as long as volume is the same. I mean, just like suppose like X is the amount of volume that like matter this like one atom takes up, right? And the volume is V. Like you have like equal amounts of V over X.
Okay, no, think about it this way, right?
No, we're done with that. We're moving
As
on.
long as the volume is
Oh, I missed something. Freddie, you got to stop. Because you just have to. The entropy of a gas will always increase as the pressure decreases. Becky, can we handle that?
I think so.
That's regardless of volume, isn't it? Or shape. I shouldn't say regardless of volume, regardless of shape. If the pressure goes down, then the entropy is going to go up.
So are you saying E1 P1 equals E2 P2?
Yes, that's what I'm saying. We won't ever use that because we're not going to calculate differences in entropy with the pressure, but that would be true. Katie, you got 10 seconds.
Alright, so if I use that
One
argument and I made like something one atom thing, but like really, really large, so large that the volume is greater than the volume of that cube, then why wouldn't that argument?
All right, we're done. Okay, thanks. Moving on.
Easier argument.
Gibbs also came up with this relationship. Gibbs has the delta G equals delta H minus T delta S. He was a pretty smart guy, and he developed this as well. The free energy of a gas, because we can measure the pressure of the gas, is equal to the standard free energy, that's a table value, plus that term right there. Ideal gas constant times temperature times the natural log of its pressure. Yes.
What does I stand for?
No, it's natural log, ln. ln.
What does that stand for?
Natural log.
Yes, every shit.
Logarithm.
Bro, it's on your calculator. It's like
E to what power? Have you not, Anthony, no natural log yet?
I don't know.
Have you done log base 10?
Wait,
What?
Yeah.
I'm out to energy.
You seriously know?
advanced or something.
Ooh.
You haven't done it?
What?
Yeah, I'm surprised. I thought.
No, they do that in like April, around that.
Well, aren't you even bad?
Okay. You haven't seen logs yet?
No, I haven't.
Oh, yeah. All right. Did you write that equation down? G equals G standard plus RT ln of P.
What's G standard? Like G in standard conditions.
Yeah, under the standard conditions.
Okay, how do you determine that?
It's in the back of the book.
It's a table there. Yeah, you just look
Okay,
at the
Abby.
table. It's constant number. So the free energy is changing as the pressure changes. Now remember that G doesn't have any physical meaning. Delta G is going to have a meaning to us, so eventually we're going to get there. Now, this is a derivation. We're going to walk together. I'm going to hold your hand, and it's going to be like we're walking through wet cement at first. You know what it's like to walk through wet cement? You could imagine walking through wet cement, right? At the end, it's very nice and pleasurable. But in the middle, it's difficult. It's not, I shouldn't even say difficult, it's tedious. So if we have, now notice that I have 3 different colors. One for my hydrogen, a different color for nitrogen, and one different color for the product. This means that the free energy of the hydrogen is equal to the standard free energy of hydrogen plus the RT ln times, or not ln times, the natural logarithm pressure of hydrogen. Hold on a second, let me get through this and then you can ask. The same thing is true for the other 2 gases, the other reactant and the product. Since they're all gases, you could give an expression for each of their free energies. Peter.
So the G under standard conditions for every compound or whatever is always the same.
Yeah. Yeah, so that's a constant number. Right.
Are we ever going to go through derivation for
We're doing it right now.
that? Or like the derivation of the X?
To get this?
Yeah.
No. I mean, the book has that. All right. You know that delta G for this reaction would be the free energy of the products minus the free energy of the reactants. So that's exactly what I have here. Now, notice that the product has a 2 coefficient, so you would have to multiply its free energy times 2. The H2 has a 3 in front of it, so you have to multiply that one too. Okay, we're down under 10 minutes left in the hour.
Okay, I think we should just stop here.
If we're getting too late, then I'll just jump to the end. But let's take a look at how we get there. I see G terms, and it looks like we have expressions for G terms. How about we make a substitution? Does that look like it's going to be messy?
No, it's not.
What?
Wait, the substitution is messy.
Good.
Oh my god.
That's not so messy, is it?
It's not.
Okay.
Pretty messy to me.
No, what's like one of those?
So this I color coded. This is the same equation that was on the bottom of the previous screen, but I color coded again to match up the colors. So we have the free energy of the product times 2 because there was a 2 coefficient, minus the total free energy of the reactants, which there's 2 of them. Ugh, I'm sorry about this. tedious, isn't it? All these repeating expressions. Okay, so now we're going to do some algebra. What do you want to do first? Go ahead.
Take all the G terms out.
Before that, let's distribute.
Don't you just do that in your head?
Nope. We're going to multiply this term through by 2, multiply that term through by 3, and there it is. You got 2 and 2 right there. You got minus 3 and 3, and then that didn't have to do any distributing. But I did distribute the negative sign. Look at what I did here. That negative sign now is distributed to every term that's inside of those brackets. So I got rid of the brackets and just went ahead and put my negative sign through all those. So I had 2 terms being added minus a whole bunch of terms. Products minus reactants. Next step, let's put the G's together. Good with you? Okay, now while you write that, I'm going to write this. 3H2 plus N2. Just want to remind you of what our chemical equation is. I just want to share that. Yeah, but that was not supposed to happen.
Well, that was a logistical.
It was a logistical error. Dude, let's go.
Oh my god! Is that blood?
He was burning hydrogen. I didn't know you.
Oh.
That scared me.
Wait, why don't we do that?
Maybe if you want to.
We derive equations. That's way better.
No, it's not.
Yeah. Okay, so I want you to consider this term. I know that I just lost you after that comment. And that term. The energy of the product minus the energy of H2 minus the energy of N2. Can we rename that? That minus those two. That's delta G. That's the overall delta G for the reaction. Standard delta G. And so that's what I'm suggesting, is that the G of this minus the G of those two gives us the standard delta G.
What's the difference between the delta G on the left?
Oh, this is at any set of conditions. That's specifically standard conditions. So maybe we have 2 atmospheres and 100 degrees Celsius or whatever. That's that one. Okay, that's a constant value. It's a table value. Now that was the worst part. The rest of it we just clean up. And I wanted you to see this next part. I think maybe you don't appreciate this, but you will. You know how you have to learn all these properties of logs and you hate it? There's a reason that you do that. What can you do with that too? Actually, I need to do one step first, and that would be take the RT out of these 3. I'm going to factor the RT out of those. And if you've been writing every step of this, we're going to run out of time. So I would say just check this out. Freddie, you got a question?
So then, wait, don't you just get like ln of like kinetics?
Yes, you do. So I've taken the RT out, just of these terms. So my delta G standard is still there. And now this blue, green, and red has now had its RT taken out, and then what's left after the RT has been taken out? What's that? Now we use the properties of the logs. That 2 out in front of there can raise up to the power on the pressure. That 3 can raise up to the power on the pressure. You've learned that before, right? Yeah.
Except for Anthony.
You've never seen that before? Nope. Man. So that's what I'm saying in the next step. Okay, another property of logs. When you have the natural log of this minus the natural log of this, is there a way that you can rewrite that? Yeah, it could be a natural log of the quotient of those two things. Now I have two things that are being subtracted. Should I put them both in the denominator? Yeah. Just put them both down there. That's what I have in the next slide. If you're trying to write this down, I'm sorry, but I have to, in the interest of time, just keep going. So it's right there. Natural log of this quantity is the same thing as what we had before. So the natural log of the products over the reactants, the pressure of the products over the pressure of the reactants, that will look familiar to you if it doesn't already. You've seen before in your chemistry life where you have to take the ratio of the products to the reactants. It's okay if you don't remember. Right now, I'm going to call that ratio of products to reactants Q. And that stands for the reaction quotient. That just tells you how much product to reactant ratio, what your product to reactant ratio is. And so that's going to be it for the hour right now. Q is the reaction quotient. It's the pressure of the products and pressure of the reactants. Kind of tells us where we are in the reaction. Karthik, he's such a funny kid. What is the Q value at the beginning of a reaction? At the very beginning? 0, because you don't have any products. You have to exert any pressure. It's just 0 over whatever the reaction products are, or pressures are. So as the reaction proceeds to the right, the Q is changing and increasing all the time. Thank you very much, everybody. Have a nice weekend.